हेलो एंड वेलकम अगेन। सो लास्ट टाइम हमने पॉइसन इक्वेशन पढ़ा था दैट वाज del square v equals to minus rho over epsilon naught. Okay, and we solved this for a special case when rho equals to 0. Then the equation we got was del square v is equals to 0 simply, right? And we solved it for two systems. So first one was the Cartesian system, and the second one was the spherical system. And today what we're going to do is to solve this equation for cylindrical system. Okay, so remember last time, um, when we were doing the Cartesian system, so then in that case the solution that we got was, suppose if our potential varies in the direction of x, so we wrote the equation we got, the solution we got was v of x equals to a x plus b. So this was the form of equation where a and b were the constants. Okay, so a was the constant, b was also the constant, which depends upon the boundary conditions. Okay, so the value of these two constants depends on the boundary conditions, right? Similarly, for spherical system we also saw the solution, and the solution was like v of r equals to a by r plus b. Again, a and b were the constants. Okay, so A and B were the constants and whose value depended on the boundary conditions that we used. Okay, so today we are going to solve this cylindrical system. Okay, so let's solve. So our equation is del square V equals to 0. Now this is a Laplacian. Okay, we know it's a Laplacian and we have to Laplacian. Okay, and we have to write the Laplacian in cylindrical coordinates. And in cylindrical coordinates, the Laplacian looks like this. So del square in cylindrical coordinates is 1 over r dou by dou r of r dou by dou r plus 1 over r square by dou phi square plus dou square by dou z square. So because we know in cylindrical system there are three coordinates. One is r, phi, and z. Okay, so we have wrote del square in terms of these three coordinates. Okay, which are perpendicular orthogonal basis vectors. So we have wrote down our Laplacian. Then what we're going to do now is to simply solve this equation. Del square v equals to 0. So what will we get? So it now again what we're going to do is to do only those kinds of solution where we have no phi and z dependency. Okay, so there is no phi and z dependency. That means this term we can drop out. Okay, so we can simply write, and because there is only one variable now r, so we can write instead of dou we can simply write d. Okay, because there is only one functional dependence, that is on r only, right? So we can write 1 over r d by dr times r d by dr of v equals to 0. So that's my this equation. Okay, right? So if we solve this equation, so let me solve it entirely. So 1 over r, this factor will go to this side and it will be simply 0. So it will be d by dr of r dv by dr equals to 0. Now what we will do, we'll do first integration. Okay, so when we'll do first integration, so it's a sum function, right? It's some function. Okay, so it's like this, d by dr of some function equals to 0. If the differential of some function is 0, that means this function must be some constant, right? So let's write that constant as a. So that means f, which is our r dv by dr, is some constant a, right? So this is the first integration basically. Then we'll do second integration. So for that, what I will do, so I will separate the variables. Okay, dv equals to a by r dr. It's just a simple separation of variables, and I will do integration on both sides, and what I will get, v equals to a. Now integration of 1 over r is ln of r plus the integration of constant. This is the second integration constant, that is b. So we have our solution, v equals to a ln of r plus b. So this is a solution in cylindrical coordinates. Now if we go back to our all solutions, so we have the third solution as well. So V for cylindrical system is simply A ln of R plus B. Okay, again A and B are constants whose value will depend on the boundary condition that we'll use in our examples. Okay, so these are the three solutions, and remember, in all these three solutions we have assumed some symmetry. Okay, now let's do some problem in this case. So let's take a simple problem. So this is problem number one. Let's take an infinitely long cylinder. Okay, there is no charges, so it's an infinitely long cylinder, right? And whose radius is capital R, and whose surface is at a potential V naught. Okay, so this infinitely long cylinder is at potential V naught. Infinitely long cylinder. Okay, whose radius is capital R and whose potential is V naught. And we'll assume one condition will apply to this problem, that at infinity potential goes to zero. Okay, so that we can solve our problem easily. Now let's solve. We know the solution, right? We know the solution, that the solution will be simply A, where A is some constant, ln of R plus B. So you are seeing the beauty of using Poisson's equation. Okay, so you just simply write down the solution, V equals to A ln of R plus B. Okay, now the only thing that we have to do is to find these two constants A and B, right? And that we'll figure out using boundary conditions. Okay, now look carefully here. So first integration, first constant we'll find very easily. So we know when when R equals to capital R, V equals to V naught, right? So we'll substitute these two things into this equation. So V के बदले V naught equals to A ln of capital R plus B. Okay, so from here we can get the value of B. Okay, so B equals to V naught minus A ln of R, right? So we have one constant. Now how to get the another constant A? So look carefully here. Now we can use one more condition, that at infinity V equals to V naught. But if you put directly here, directly into this equation, suppose R goes to infinity, then V will go to infinity, which doesn't seem to be the case, because we know at infinity V has to go to zero. So we will not put directly into this equation. What we'll do, we'll solve this equation a bit. Okay, so we'll write V equals to A ln of R plus, so we know B is here, so it's V naught minus A ln of R. Okay, so what I'm doing here, basically I want to plug in this condition. So for that I will solve my this first equation a bit. So now let's do some separation here. So I can write A, so this term and this term, I'm taking A constant, so what I'll get, A ln of R by capital R, because we know ln of R minus ln of capital R will be simply ln of R by capital R. Okay, and plus V naught. So this is my equation, but still A has to be find out. Okay, I have not find out what is the value of A. So how to find it? We can use boundary condition now. Now we can use a boundary condition. See, when R goes to infinity, V has to go to zero. Now if we look here, when R goes to infinity, ln of infinity will go to infinity, because ln of infinity is also infinity. So what do I have to do? So if V has to go to zero, if this V has to go to zero, then that means this whole term has to go to minus V naught. If this goes to minus V naught, then we have plus V naught, then minus V naught plus V naught will give me 0. So that means to apply this condition means A ln of R by capital R has to go to minus V naught, right? So this is the beauty of this trick. So A ln of small r by capital R has to go to minus V naught. Only then we can see this condition to be applied here. Okay, so that means A will be equals to minus V naught by ln of small r by capital R. Now we have both the constants. I have A and I have B also. Okay, and we can substitute into our final equation, that is V equals to A ln of R plus B.